All right, folks, we just had a long video about a bunch of different properties of summation and some summation formulas that we're going to need to use. So now it's time to show you how we're going to be actually using these. So I'm not going to do like a complete problem. I'm just going to do an example which isolates the particular skill that I'm teaching you right now. Okay, so we're going to get to this idea of area and stuff later on, but for now, let's just finish up. Let's wrap up this. We're going to wrap up the study of summation notation by doing this example. So there's two parts to this problem. The first part is inside here. So the first thing we're going to do is take that sum, and we're going to evaluate that sum. Then we're going to take the result that we get, and we're going to take a limit as n approaches infinity. Okay, so I'm going to do this in two parts. So first we have this. The sum from I equals 1 to n of I plus 1 over n squared. First thing to point out about this is that I is the variable. N should be treated as if it is a constant in the context of this sum. Because for all the terms in this sum, the only thing that's changing is the value of I, right? I goes from 1 up to n. The value of n is not changing. N should be thought of as essentially fixed at the moment. So that divided by n squared, that is like a constant multiple. It might as well be multiplied by 1 over n squared and then factor that out of the entire sum. So the first thing I'm going to do is apply the constant multiple rule to factor out 1 over n squared, leaving us with a sum I equals 1 to n of I plus 1, like that. So that, first of all, I hope that makes sense. The idea is that as far as the sum is concerned, n might as well be constant because this is a sum over the index I. So I is the variable, and within each term, I is the thing that's changing, nothing else. So now that we've factored out the 1 over n squared, now we can use the sum rule. So let's split this sum over the addition here. Essentially, basically just using the commutative and technically, I forgot to mention this in the last video, but also the associative property of addition to sort of rearrange that sum into sum from 1 to n of I, and then plus the sum from 1 to n of 1. There we go. Okay, now it's time to get in here and use a couple of summation formulas. So for this part right here, we have the summation formula, but that's going to be n times n plus 1 over 2. Summing up I from 1 to n, like 1 plus 2 plus 3 plus 4, all the way up to n, gives us this formula. All right, so that's a closed formula. We can just replace this term entirely by n times n plus 1 over 2. And then this other one over here, summing from 1 to n, the number 1, that's just 1 plus 1 plus 1 plus 1 plus 1, n times, so that's just going to equal n. So our next step is to do both of these substitutions and simplify this up a lot. So this is 1 over n squared times n times n plus 1 over 2 plus n. Now let's just simplify this result slightly. Let's distribute the multiplication by n squared. So we're going to have n times n plus 1 over 2n squared, and then plus n over n squared. There's a little bit of canceling that can happen here. One of these n's cancels with this one. This n cancels with this one, leaving us with... and then we can actually... Let's combine these into one term as well. Let's multiply this by 2 over 2. Giving us a denominator of 2n. And then we have n plus 1 plus 2n. No, sorry, plus 2. The n canceled out, my bad. So this leaves us with simplified n plus 3 over 2n. All right, so that's most of the work. We have this, which gets to go back inside here, right? We've evaluated the sum and simplified it. So now we can do the limit as n approaches infinity of this n plus 3 over 2n, which, if we do the 1 over n trick like this, we can write this as 1 plus 3 over n divided by 2. And as n goes to infinity, this term is going to approach 0, so the resulting limit will be 1/2. And we did it. So there you go. That's an example of the type of thing we're going to do. Now we're going to talk about area Okay, we're going to talk about that whole idea of adding up rectangles to approximate an area, and then we're going to take a limit as the number of rectangles approaches infinity. See where this is going? Number of rectangles is going to approach infinity, and then we'll be able to calculate exact area underneath a curve.